While a typical wing will struggle to produce lift efficiently above 15 degrees or so, delta wings can produce lift efficiently over 50, 60, or even 70 degrees. And since the discovery of delta wings, they've found a home on some of the most advanced aircraft ever, largely for that reason, for example, fighter jets. But believe it or not, delta wings are kind of outdated now. We've kind of moved beyond them, and it's pretty rare to see such a simple geometry now. In fact, we usually see things like a triple delta wing, as we can see here in figure 4. So on the left, we see one geometry in gray, and then on the right, we see another geometry in the reddy orange. The gray geometry has 3 distinct angles to its wing's leading edge. At the front, the angle is relatively flat. Then there is this middle section where the leading edge is relatively slanted. Then the rest of the wing where the leading edge goes back to being relatively flat again, although it is still quite slanted. So the design is quite complicated, and the resulting aerodynamics are too. So for example, in figure 7, as we saw before, we saw the vortices rolling up, and there are a bunch over here. And actually, what we see is, in this figure, it isn't the most complicated that it can be either. Actually, there can be even more vortices off the nose of the plane too that interact with the rest of the wing as well. So here we don't have those. So while the basic delta wing produces one main vortex on each side, here we get multiple on each side. But so what? What's the point? Well, in this podcast, that's what we're going to find out. And we'll see the effects of these vortices from this triple delta wing and that configuration. And there's also the second configuration, which was a double delta wing on the lift and drag on the flow field as well. So to do that, we're looking at this research called Numerical Investigation of Vortex Formation on a Generic Multiple Sweep Angle Configuration. It's open access, so you can find the link below, and the DOI is at the top left of the page. And one interesting thing about this is, not only did they look at the flow physics of these geometries, but they also looked at the accuracy of a couple different ways of simulating them. So in fact, when it comes to multi-swept wings and transonic speeds, accurately simulating them becomes quite challenging. And if you'd like to see some simulations on them, then check out a video we did on the Eurofighter at transonic speeds here. Let's now jump to the method that these researchers used. And if you want to see the results, then jump to this time step instead. Otherwise, let's continue now with the method. So in figure 1, we see 2 different plan forms the authors looked at. On the left is the triple swept delta wing, and then on the right is the double swept delta wing. Now, one question that may arise is, why? Why do you need swept leading edges, especially to produce vortices? Well, the answer is that you don't actually need swept leading edges. You actually need swept leading edges with sharp leading edges too, together. That then allows the flow to roll up over them and into vortices. And these vortices then travel over the wing's upper surface, and because they are low pressure cores, that then pulls the rest of the air above them down. That then results in that air being able to stay attached far more easily over that surface. As a result, the delta wing can then pitch to much higher angles of attack and still maintain mostly attached flow, as well as produce lift efficiently. When we have 2 or 3 angles, then the plethora of vortices produced occur, and they suck down the air over the top surface much more efficiently and effectively, and that increases lift in a more robust fashion, as we'll see later. Now, the main difference between the triple delta wing and the double delta wing is that obviously the triple delta wing has additional delta parts, but the angles of the leading edges are still the same. So what I mean by that is here, for the double delta wing, there are 2 angles. The first leading edge has a sweep angle of 75 degrees, while the second leading edge has a sweep angle of 52.5 degrees. For the triple delta wing, the same angles are used, it's just that the first delta leading edge part now is 52.5 degrees, then the second one is 75 degrees, and then the third one is back to 52.5 degrees again. So all that has happened is that an additional leading edge has snuck in the front there. And because they are using CFD to simulate these geometries, the mesh they used is very important. So in figure 2, we see some cross-sectional cuts of the geometry. And the authors say that they used a boundary layer mesh of 33 layers and gave the Y plus value of 1 or less. So is that a good Y plus value? Well, they used the Spalart-Almaras turbulence model, but it wasn't the original Spalart-Almaras version. They actually used an improved version with rotational correction. That's good because that greatly improves its accuracy, and a Y plus value of 1 is good for that approach then. Now, they used URAN, and DDDS, and the DDDS version should give better results, at least in theory, but we'll see later if that's the case. We'll see if the URAN's approach could really handle this flow or not. But from what I can tell here, they only used an incompressible approach, and they also say that the maximum velocity considered here was 130 meters per second. Now, this is about the point at which it is conventionally agreed upon that the flow changes from incompressible to compressible. But in this video on our YouTube channel, we actually go through the equations describing the density of air with velocity and show that even at Mach 0.1, considerable compressibility effects occur, and perhaps that's a point now to change from incompressible to compressible flows. Anyway, to see how many cells they needed to use, the authors used a grid-independent study, which is really good. We can see the results in figure 3 here. So some notes about this is first, the angle tested was 16 degrees, and then it was for the double delta geometry. They then chose the lift, drag, and pitching moment coefficients as the metrics to determine how many cells are required. So this is very thoroughly done, and well done to the authors. They tested from 12 million cells up to 110 million cells. That's quite a lot, especially considering that their time step was very small, just 7 microseconds. And then they used hundreds of inner iterations per time step. Now, what that last bit means is that as you iterate through the times each time step, you then halt, then iterate through without changing that time step, and then once you reach the desired criteria for convergence within that time step, you then stop the inner iterations, jump to the next time step, and then do the same thing. So it's kind of like a quasi-static transient approach, which is pretty much how you do transient simulations anyway. So at 110 million cells, it would take a couple of days on a cluster of like 1000 cores to do a simulation still, so that's quite a lot. Now, in figure 3, we see the CFD results and the experimental data. So this is not just a grid convergence study, but also a validation study as well, which is great. First of all, the grid convergence though. So once about 52 million cells are reached, the lift and pitching moment coefficients don't really change too much. So this is kind of the point where the grid is converged for those metrics. Maybe there's a couple of tenths of % deviation from there on. But for the drag coefficient still, that deviates a little more after that, so maybe about 0.5% or so. Even still, that's very good, and the simulations seem to have converged across the board, so 52 million cells seem to be the grid that they can use. And comparing their results to the experimental data now, the CFD is pretty good. So there's consistently about a % off or so among the lift, drag, and pitching moment coefficients, and that's very good. Getting to within a % accuracy for CFD is very challenging, especially for such a geometry. And it's still a little easier because things are still very subsonic, but still for such a complex geometry and with a lot of flow physics going on, that's very difficult to do. Now, as a side note, one of the best CFD softwares is OpenFOAM. If you'd like to learn OpenFOAM, then check out our courses here. And back to these results. So from the validation study and the grid convergence study, we can really trust the CFD to within a % or so for the force results. For the flow physics, we'll see a little more later on as well. And speaking of such, let's now jump to the results in general. So in figure 5, we see the lift and pitching moment coefficients for the triple delta wing. So this gray left part, which they just mirrored, so they have a complete wing. And these are the results on this plot here. And we see the results from the experiments to the URAN CFD and then to the DES CFD, or DDDS more accurately. So the squares are the lift coefficient, and now we see just why delta wings in general are so useful. Looking at the x-axis, we can see the angle of attack. It goes from 0 degrees up to 40 degrees, and the lift coefficient is good up until about 30 degrees. From there, its performance degrades, which suggests that the vortices are bursting quite far upstream, hence most of the wing isn't experiencing the vortex lift phenomenon that delta wings produce. But still up to 30 degrees, the wings produce a good lift, and even higher, the actual lift coefficient still is good, but you just have a drop off in terms of its performance. Now, one thing you might notice is that while the wing produces good lift up to about 30 degrees, and even higher really, the actual lift coefficient value isn't any higher than a typical wing. Values up to about 1.5 are seen here, which are well within the range of regular wings still. So we can see that here the delta wing doesn't really increase the maximum lift coefficient produced, but rather they just extend the range that the wing produces lift over. Another interesting thing is that the pitching moment, which we see in the triangles. So two things that stand out here are first, the slope of the pitching moment coefficient is positive. That means that the wing is naturally unstable in the pitching direction. That's because a positive slope means that the higher the angle of attack you pitch your wing to, the more it wants to pitch up. At a certain point, you're going to run out of angles of attack that you can go to produce good lift still, and then you'll stall. You'll then have a harder time controlling the plane from there. The second thing that stands out is that at around 12 degrees or so, the pitching moment coefficient all of a sudden just takes off, and the slope is like 3 times greater than at lower angles of attack. This will definitely make the plane harder to control because you'll get this sudden jolt that makes your plane want to pitch up way more. And I think the reason why we get this inflection here is because at this angle, the vortices produced, which are quite strong, they will probably become stronger and the vortex lift effect maybe becomes more prominent, and or maybe some vortex bursting occurs too. We'll get more into that later on. Anyway, in terms of how the CFD is performing, the DDDS, so the blue symbols, are doing very well. They lie right on the experimental data. The URANs are pretty good too, but still a little off. And what I would like to see is the point at which the pitching moment dramatically changes, so around 12 degrees to be simulated. That's because there is obviously an important flow phenomenon happening right here. And if the CFD picked it up right at this point, then that would be very impressive, because it's a very delicate thing that flow physics change at that particular angle of attack. If you can simulate it in CFD and match it with your CFD, that's just very impressive. That's very difficult to do. Usually you might have like a tenth of a degree difference, or maybe even a degree difference to when this occurs. But if you were to get it right on that point, then that would be like incredibly impressive for the CFD. Right now the CFD is picking it up, but we don't know if it's getting the exact angle right or not, because the angle that the author simulated was 16 degrees, and that's already a little past the point at which this inflection point occurs. But it's still very impressive. So in figure 6, we see the flow viz of the triple delta wing. It's a little complicated, so let's explain what we're seeing here. So the left column is the experimental results, the middle column is for the URAN's CFD results, the right column is for the DDDS CFD results. The actual quantity plotted here is the normalized free stream direction velocity. In other words, the speed of the flow in the free stream direction divided by the free stream speed. 1 corresponds to green in this color plot, means that the flow at this point is the same speed as the free stream flow. Then we have a bunch of rows. They correspond to different locations down the delta wing. So on the top left of each row, we see the location as a decimal of the chord. For example, 0.125 means 12.5% back from the leading edge. We also see the outline of the plane in a thin black line next to the number. And looking at the experimental results, it's the left column. Interestingly, despite there being 3 delta wing leading edges, only 2 main vortices seem to be forming. And in figure 7 actually, we can clearly see that happening. So there is 1 vortex from each of from the very start of the first leading edge, and then that manages to stay intact pretty well down the entire chord of the wing, down to the trailing edge. But the second delta leading edge doesn't produce a vortex. Instead, actually, the second vortex starts from the junction of the second and third leading edges. These 2 vortices meet and then start to roll up together. But the interesting thing is that if we compare these vortices formations with the double delta wing, which we can see in figure 14, if we scroll down here. So figure 7 had 2 vortices for the triple delta wing. Figure 14 has a double delta wing, but still produces 2 vortices on each wing. But the vortices interact a little differently. So the same number of vortices are produced, but they form differently here. The first vortex forms, but it's constantly fed by the leading edge. You can see how all this flow is just continually being wrapped up from the leading edge. The second vortex forms at the junction between the 2 leading edges, but it's not tight. it's not crisp like we saw with the triple delta wing, but instead it's kind of, again, forming as you continue down the leading edge. But how does that difference in the vortices formations affect the performance of the wing? Well, looking at figure 12, where we see the lift and pitching moment coefficients, the results are very different. So first of all, the lift coefficient, this is for the double delta wing, its performance starts to plateau at around 22 degrees. That's much lower than the 30-degree point we saw for the triple delta wing. And the lift coefficient here is only about 1.3-ish, while the triple delta wing achieved up to 1.5. So the lift coefficient is lower here, the maximum, but the triple delta wing had a typical stall pattern where after the maximum lift coefficient, so if we scroll back up to that plot, we can see that it's a pretty conventional stall pattern. After that maximum lift coefficient, the lift coefficient then started to drop off. For the double delta wing in figure 12, we don't get that drop off. In fact, here we go. It's pretty much plateauing. And I think the reason for that is the vortex formations we saw in figure 14, because the vortices are constantly being fed by leading edges, even if there is a little bit of stall, the vortices are just continuing to be fueled, which means that they can continue to produce vortex lift. So it seems like this double delta wing configuration here, while it doesn't reach the same peak performance as the triple delta wing in its lift coefficient, its performance is more stable. And speaking of stable, looking at the pitching moment coefficients, things are much better for this double delta wing. So in this figure, before we get to the lift coefficient plateauing, we get a negative slope for the pitching moment coefficient. That means that the wing is stable. And this is the exact opposite to the triple delta wing, where in that figure, we saw that, here we go, across angle attack range, the pitching moment coefficient slope was positive. So this wing is much more stable for the pre-plateau / stall angles if it has a double delta wing instead of a triple delta wing. Now, post 22 degrees, the story changes and the pitching moment coefficient slope becomes more positive. That means the wing is inherently unstable. Now, the reason why I think we get such a reversal of the slope pre-22 degrees compared to post-22 degrees is because the vortices start to burst at these high angles of attack. What that means is, looking back at figure 14, while this was for a 16-degree angle of attack, as angle attack increases, the vortices will start to pop near the trailing edge. Then as angle attack increases, the point at which the vortices burst will move forward. That means that as angle attack increases, the amount of lift produced towards the trailing edge will start to reduce. That affects the pitching moment because the pitching moment tells us how much the wing wants to tilt forwards or backwards. If you produce more lift at the rear part of the wing, then the wing will want to pitch down more, which means negative pitching moment. If you produce less lift at the rear of the part of the wing, then the wing will want to pitch up more. Here, if the pitching moment is reducing with increasing angle of attack, it means that, relatively speaking, there is probably more lift produced at the rear of the wing. So that might be because the vortices are starting to burst there. So here there are two phases. The part where the pitching moment is reducing, so that's pre-22 degrees, that suggests that less lift is produced at the rear of the wing. Hence vortices are still intact and decent lift is produced there still. Then there is post-22 degrees, which is where the vortices burst and there is less lift in the rear. For figure 5, we saw for the triple delta wing that the pitching moment coefficient started to increase a lot at around 12 degrees, which again could just be because the vortices are getting stronger, or it could be because they're starting to burst there a little more. We're not too sure because we don't have the flow physics there, but both are possible. I think it's probably bursting after seeing that figure 12 as well. And that would make sense because looking at figure 7, because the vortices aren't being continually fueled by the leading edges, so they aren't being strengthened continually, that means that they are probably more susceptible to bursting sooner, I would imagine, down towards the trailing edge. And actually in this figure, towards the trailing edge, we can kind of see that a little bit, I reckon. I think there's a little bit of bursting going on there. And just as a quick note on this kind of stuff, so airplane aerodynamics, if you'd like to learn more about it and even how to design your own airplanes, then check out our brand new course on airplane design here. Let's now get into which is a better delta wing though. So looking at these two graphs, which one would be better? The first one has a better pitching moment, worse pitching moment, but better lift coefficient. This one has a better pitching moment, but worse lift coefficient, but it really depends on what you want. So if you can correct for the pitching moment coefficient of the triple delta wing, so you might get a tail on the back or canards or whatever you like to do, then you might want to go for the one that has more lift. But if you want to have a more robust wing, then perhaps the double delta wing is better because you have more consistent lift coefficient at higher angle of attack, the pitching moment is more stable, and that's the major benefit of this double delta wing. But one thing that it could be better at is as the pitching moment crosses the x-axis, we don't have that currently, so you can see that at all these angles of attack, the pitching moment is above the x-axis. If you could get the pitching moment to cross it, then at some point there would be a pitching moment of 0. That way you'd have an angle of attack that the wing would naturally want to bounce back to. And it would be even better if you could make that point at which it crosses the x-axis the angle of attack you want to perform most at. That way you can sort of cruise or whatever you want to do at that angle of attack, and it wants to stay at that angle of attack much more readily than any other angle of attack. That'll make it far easier to control. So the double delta wing is probably better overall in its performance, but there would be situations where maybe the triple delta wing would be better if you want to get higher lift and you can make the wing more stable anyway. And with that, we come to the end of this podcast. It was very interesting to see a simpler wing, such as a double delta wing, perform better than a more complex triple delta wing. And if you'd like to learn more about airplane aerodynamics and even how to design your own airplanes and then to build them and fly little UAVs and that, then check out our brand new course where we just launched it here. And if you'd like us to simulate your very own car, let us know below. And if you'd like to learn CFD and in particular OpenFOAM, which is a completely free and powerful CFD software, then check out our courses here. And if you want to learn more about delta wings, then watch this podcast episode here. Peace out, amigos.